Okay, so I think we're live on the stream. Okay, so just maybe wait 1 or 2 more minutes and then we can get started. I will stop the stream and the recording after you're done with the talk, so we can keep the Q&A off the record, so people might feel a bit more encouraged to turn on their video and ask questions. But okay, let me just. Okay. Great. Okay. All right. Good afternoon or good morning, good evening, wherever you are. Thank you so much for joining us on Zoom or YouTube, and thank you, Nando, very much for donating your time to for this talk. It's really a pleasure to host you, although virtually. So just a very quick introduction. So Ferdinando is an assistant professor at Syracuse University. Has been doing a lot of work on optimization, differential privacy, and machine learning, as you will see in his talk today. And so really his recent work has been focusing on making AI algorithms better aligned with societal values, especially privacy and fairness, and how to integrate machine learning with optimization to solve complex optimization problems. He has won a few accolades, the Mario Gerla Young Investigator Award, Early Career Researcher Award by the Association for Constrained Programming, the Best AI Dissertation, and various Best Paper Awards. He's also been co-organizer of the AAI Privacy Preserving AI Workshop. And well, without further ado, thank you so much. Please take it away. Thanks.
Thank you, Milano, for the nice introduction. So I'm going to share my screen. Assuming you'll see my screen, right?
Yeah, perfect.
Perfect. Thanks for the nice introduction, and I'm really happy to be presenting at this seminar, where today I'm going to discuss some of the views on privacy and fairness and the recent development in this area, especially from my group. So just to set the tone, optimization and learning systems have become instrumental for many decisions and policy operations which are involving individuals. And so this includes assisting in legal decisions, determination related to whether an individuals qualify for some benefits, such as loans, or assigning resources to entities or individuals. So those are just a few examples, and often the success that is associated to this technology here is really the presence of rich data sets which contains identifiable information. But the use of these rich data sets combined with the adoption of black box algorithms has also sparked concerns about how the systems operate. And two key concerns regard how much information the systems leak about individuals whose data is used as inputs, and also how do they handle discrimination. So for the former, differential privacy has become the paradigm of choice for protecting data privacy. And we have seen that its deployments growing at a fast rate. And so they involve the release of many data products by the 2020 Census, Google Gboard, which is a virtual keyboard using predictive type engine that uses differential privacy and federated learning for training model privately. Facebook has used differential privacy to release large data sets to support academic research on social media roles in elections. Apple's Uber. So we have seen many deployments of differential privacy in practice. And differential privacy is really appealing because it bounds the risk of disclosing sensitive information of individuals which are participating into a computation. But this process to render the data or the model, the output privacy preserving, may also fundamentally impacts some important properties of the outputs. And in particular, it was recently recognized that differential privacy systems might induce or exacerbate bias and unfairness outcomes for different subgroups of individuals. And the resulting outcomes can have significant societal and economic impacts on those individuals. And to give you an example, this is the Title I of the Elementary and Secondary Act, which is one of the largest US program. It offers educational assistance to disadvantaged children. In 2015, for example, it distributed 6.5 billion through basic grants. So this federal allotment is divided among qualifying school districts in proportions to the count XI of children in the district. So for those of you that do not live in the US, here essentially school districts includes a subset of schools that you have in your town, and each school district has different properties in terms of cost, in terms of education, number of teachers and students and so on. And so this allotment here divides the quantity proportionally to various school districts, and this number here of students counts the number of students in these districts which are qualified. In a sense, their family fall below certain the poverty level line, or they receive some form of federal financial aid in that district. And so this allotment here represents a proportion of that money multiplied by a constant, where this constant represents the student expenditure in that district. So if we look at this figure here on the right, it illustrates the expected disparity errors which are arising when we're using the privacy preserving data as input to this allocation problem. And those errors are expressed in terms of US dollars misallocation across different New York school districts ordered by their sizes. And as you can observe here, some school districts may receive up to, in this case, $42,000 less than warranted for this privacy choice. And thus they might result in large fairness issues. Other examples were noticed also in ML systems, firstly by Bagdasaryan et al. In 2019. They measure the accuracy of differential privacy in a gender and age classification task on facial images and on sentiment analysis of tweets. So here the groups analyzed have lighter and darker skin tones for the first task, and the standard American English versus African American English for the second task. And what they showed empirically is that differential privacy might affect the accuracy of the minority subgroups, so more than the accuracy of the majority subgroup. And so those outcomes here can have significant societal impacts on the resulting groups or individuals, as classification errors may penalize some groups over others in important determinations. Biased decisions can result in disparities regarding allocation of critical funds, benefits, therapeutics, as we will see next. And now, while those observations have become more apparent in several contexts now, their causes are largely understudied and I believe not fully understood. And so it is the goal of this talk to shed some light on those observations, try to understand why those observations are arising. And we're going to do it by studying two settings. In the first setting, we focus on data release task. So we have a data set which contains some sensitive data of individuals, and we're going to use a privacy preserving mechanism to release a differentially private version of this data set, and then use this data as input to an allocation problem. And we want to understand what are the impacts of those allocations in terms of fairness. In the second setting, we're going to use privacy preserving machine learning task. And here we want to study the impact of the results of the outputs of this task in terms of fairness. And so this is the outline. We will review briefly the data release setting and differential privacy, and then we'll dive into the understanding the reasons why fairness arises in decision-making and in machine learning tasks, which preserve differential privacy. And I will conclude then with some remarks. So let's get started with counting and self-publishing. And I'm going to take a census data release perspective for the majority of my talk here. So every 10 years in, well, the United States, US Census Bureau surveys the American population with the goal of counting every person living in the United States and collect information about them, like age, gender, race, ethnicity. And so the US decennial census, like other census in other countries, is an actual enumeration of the total population living in that country rather than a sample. And the data collected is extremely important because it serves for a variety of crucial tasks, such as determining the number of seats each state has in the US House of Representatives based on the share of population, redrawing district maps for the electoral colleges. It is also used to distribute $1.3 trillion in federal funds to different programs in local communities. So having an accurate count, it's extremely important. But the US Census is also required to retain confidentiality of the data collected, and this is due by law, by Title 13. And so to do so, the census has coped with a variety of disclosing avoidance techniques since the 1940s. They include data suppression, shuffling, anonymization, but also in the recent years, attackers have become more powerful, and so they started presenting privacy risks for the current releases that were not maybe present in the past. And as an evidence of such threat, the US Census has carried a few years back an attack on its own 2010 data release, which was anonymized with the same techniques used in the past and carried a linkage attack. So what is a linkage attack? Here we try to re-identify the correct statistics about the original data by solely using auxiliary information coming from public data. And so it turns out that by doing so, you can reconstruct exactly the numbers, so the census block for all the block count in the country. You can reconstruct block count, sex, age, race, and ethnicity. So for 142 million people, and this number bumps up to 219 million people, so more than 2/3 of the population if you allow a slack of 1 year in their age. And you can re-identify uniquely 118 million people, which includes their names. So this is a huge privacy concern, and it led the US Census to adopt differential privacy to protect their data. So just to review very briefly the definition, I think the audience is fairly accustomed to it. Differential privacy is a property of an algorithm. We can think it in this way. So let's think that we have two instances of a word. In an instance of this word, you have a data set, D1, that does not contain your data. In a second instance, you have the same data sets, D1, except that now you also have an additional entry, which includes your own data. And so we say that an algorithms satisfy absolute differential privacy if for a given output, the probability of generating that output from the word where your data was not in is similar to that of generating that output from the word where your data was in. And this similarity is measured in terms of a constant epsilon, which determines the risk of a user to join the data set. So more precisely, what we're bounding here is the log ratio of those two probability by epsilon. And the intuition is that an adversary that observes the output of this mechanism should not really be able to infer whether that output was generated via a data set that contained your data or not. And so why differential privacy is so cool? Well, we have a few interesting properties that we can preserve. So firstly, it is immune to linkage attacks, meaning that no matter what auxiliary knowledge an attacker might obtain, the leak of privacy does not go beyond what the algorithm, what the definition promises. So the adversary cannot reconstruct any additional information from with respect to what he already knows. It is also enjoying composability. So if we have several algorithms that satisfy some epsilon differential privacy properties, we can compose them and the privacy loss degrades gracefully. And importantly, it is also immune to post-processing, meaning that once we have access to an output generated from a differential private algorithm, we can post-process that output. And as long as this function that we're using to post-processing the output is data independent, then we can guarantee that the resulting post-processed output is also differentially private. So we're now going to dive in to try to understand the fairness impact of differential privacy in Downstream's decision. And so the focus here is to study the effect of a differentially private data release mechanism, which will essentially add noise to the input data to generate a privacy-preserving counterpart x tilde of this input data x. And so we want to study the effects on the privacy mechanism on top of the results of the an allocation problem. And so you can think of X as a data sets containing some measurable quantity of individuals, like maybe their counts. And so once again, in order to preserve privacy, typical algorithms induce some calibrated noise on top of this data. We're going to consider this noise coming from some symmetric distribution. And we will consider two classes of decision-making problems. We call them allotment problems, which are problems that distributes resources to a finite set of entities, such as representing the amount of money allotted to school districts, and decision rules, which are 0-1 decisions, and so they determine whether an entity qualifies for some benefits or not. So because random noise is added to the original data set, the output of this allocation problem here may incur some error. And so the goal here is to characterize this disparate impacts of the error among various problem entities. And to do so, we're going to focus on the problem bias, which characterizes the distance between the expected privacy-preserving allocation and the original allocation. And the expectation here is defined over the randomness of the privacy-preserving mechanism. So we'll use this definition of alpha fairness. So what we want to do is to bound the maximal differences in biases across all entities, across all individuals in our data. So we're going to focus now on understanding those effects on these classes of problems. As I showed you earlier, applying a simple allocation rule on top of noisy data may produce some severely biased decisions with significant fairness issues. And now, take in mind that this data here is produced with an unbiased mechanism, right? So there's no other step being applied there. And so what this is telling us is that even the bias really comes from not the data, but the problem itself. So the first result that I want to discuss, which we showed last year in HCI, notice that it is the shape of the decision problem which really characterizes the unfairness of some of the outcomes. And so the result here, in a nutshell, tell us that the bias can be approximated by an expression which involves the local curvature of the problem at a particular entity and the variance of the noisy input. And so fairness then can be bounded whenever the problem local curvature is constant across entities, since the variance is also constant and bounded. And so what this implies is that perfect fairness cannot be achieved whenever P is any non-convex function. And as is the case for all the motivating problems that we have treated. And so adding Laplace, Gaussian, and any symmetric, on any noise coming from a symmetric distribution, like we're used to do, necessarily will introduce some fairness issue here, despite this noise being unbiased. And so this is a negative result, but it also motivated us to develop some mitigation strategy to mitigate such type of issues. A corollary of the previous result is that if P is linear, so if the allocation problem is linear, then the resulting mechanism will also be perfectly fair with respect to this problem. And so what we can do here, by again observing that this is not a data issue, but is a problem issue, is try to linearize the resulting problem, so the resulting decision-making problem. And so we're going to use a proxy linear problem then to redistribute resources. Now, there are many ways of doing that. For these classes of problems, which distribute resources in this proportional way, what we can notice is that this problem here, it's linear in X, but it's not linear only because of the presence of this denominator. So if we were to render this denominator here constant, then the whole problem will become linear. And we can do so by either releasing the denominator publicly at a cost of typically small privacy leakage, or by releasing a noisy version of it. And if we do so, and we compare the differences of the unfairness on the original method in purple with respect to this linear method here, this linear proxy method in green, well, obviously there is large differences in fairness bounds, because now we can guarantee that the linear proxy has no fairness issues. But also importantly, when we're looking at the absolute errors, the mean absolute errors, we can notice that the purple and the green ones bars have very similar magnitude. So that is interesting because there is not much loss. So we've also looked at other classes of problems, those decision rules, which are just binary problems. And as one important problem in this class, we're going to focus on the Voting Rights Acts of the 1965, which provides protection for racial and language minorities. So this is a coverage which is determined by the census every 5 years, and it estimates that it was estimated that about 22 million people were affected by this benefits here during the 2020 election. And so the section 203 describes the condition under which local jurisdiction might provide minority language voting assistance during an election. And in particular, a jurisdiction I must provide language assistance, which include translating voting registration, ballots, and instruction in the minority language of interest, if this decision rule here returns true. And this decision rule relates various quantity of interest, like the number of people in that jurisdiction speaking the minority language of interest, those that in addition have some limited English proficiency, and those that in addition have low grade education. Now, if we look at this figure on the right, here we are illustrating the decision errors on the y-axis for the Hispanic language and sorted by the population speaking that language in the jurisdictions. And so the errors are in the true positives, which are particularly important because misclassification here implies potentially disenfranchising groups of individuals. And so the figure shows that there are significant disparities in decision errors that you can make. And importantly, those errors strongly correlate to the distance to this threshold. And so this is really interesting, I mean, because essentially what this tells you is that just because you're living in a region where the underlying population has these characteristics, so it's closer to a set arbitrary set threshold, then you might be more impacted by errors in receiving or not receiving a given benefit. And so we ask why this is happening. And so analyzing this setting here, it's more complex because the functions here are highly discontinuous. So we cannot really rely on the assumptions that we've used to build the previous result. But we start looking at components of this type of decision rules. And so one of the first things that we notice are those ratio functions. So those ratios we look at some counties that essentially have very similar ratios. And we give an example here of 3 counties that have very similar ratio, about 0.5, and their true values is outlined with blue dots. But then when we're adding noise to the inputs and we are plotting the expected ratios, then we can see that some counties have much higher bias with respect to others. So you would like this red cross here to be on the blue dot in order to have an unbiased ratio estimate. And so this was a bit puzzling at the beginning, but then inspecting the reasons why this was happening, we got that numerator and denominator for some regions were substantially different from those of other regions, despite the ratios being similar. And thus, by perturbing by small amount, smaller numerator and denominator, we can cause larger sensitivity issues than if we have larger numerator and denominators. So again, there is this kind of link with robustness, which I already mentioned earlier. And a second surprising result that we found in this context here relates to composition. So composition is a really desirable property of differential privacy. And thus we asked whether some form of composition still hold when we are analyzing the disparate impact of DP in decision processes. Well, it turns out that when you are composing predicates, the resulting unfairness it's typically larger than the unfairness of the individual components. So this is illustrated in this figure where we're showing with the pink dot and the blue dot the unfairness reached by 2 predicates in this formula, and the green dot shows the unfairness of the resulting composition when those 2 propositions are combined using logical connector AND. So you can see that the bias here, the absolute bias here, it's much larger. This holds for any connector actually, and so here we can show that the resulting unfairness here is larger than the max of the unfairness of the composing predicates. So we have the lower bound here. We don't yet have an upper bound on it, and so this is this is a kind of a sad result, because it essentially tells us that the more complex the formula might get, and the worse the unfairness might result. So what can we do here in this context? Again, this is a much more difficult scenario, but we try to resort to the same linear approximation trick that we used earlier. And so what we try to do here is, so for this problem, we have individuals that are described by several quantities. Like the particular jurisdiction is described by the number of people speaking the minority language, those that have English proficiency, and so on. So we take those features and we train a linear classifier on top of them, with the classification output being as whether they are going to receive the benefits or not. And so we are training linear classifier using linear model, linear regression or support vector machine. And then we're using the weights of these classifiers to approximate the original problem. So this can be done privately. And so what we observe is that if we plot here with the purple bars the unfairness achieved over these determinations using the original methods, so the data release, and then we are using this linearization trick, we can have some reduction in unfairness, but it's not really substantial. But this reduction gets substantial when we partition the data sets into more meaningful parts. And so we create a piecewise proxy function. So now we cannot really ensure that we're going to achieve zero fairness everywhere. We can ensure that we can achieve zero fairness within each of this proxy function here. Although this is done privately, so you don't see the zero fairness arising, but you can see a reduction on the fairness, which is quite impactful. So let us, so far we have seen issues that they really seem inherent to the problem shape and the way this decision problem is made. But we also ask whether there is more. And so let us take a step back here and look at a typical data release problem. So we have worked so far with noisy data, which is produced by a privacy preserving mechanism. And when you're releasing this noisy data may not satisfy some invariants that are present, such as non-negativity of the counts or other problem-specific properties. Those typical data release algorithms, including those adopted by the Census, use a post-processing step, which is used to re-establish those data invariants onto the noisy data. So this step here in our algorithms is essentially cast as a projection that redistributes the noise to satisfy those invariants. So it projects the new variables onto some meaningful feasible region. So for instance, in the case of the Census, the data counts released at the level of the states needs to be consistent with the counts at the level of the counties, as well as we want those counts to be negative. So what we do, we minimize the deviations of the noisy data subject to the problem constraints. And we consider some constraints which enforce dependency of the parent with respect to the sum of the counts of the children and non-negativity constraints. So we know this program will satisfy differential privacy due to post-processing immunity, but some really interesting effects will arise here. So if we consider this plot of counts where we have frequency by certain indexes of those counts, and we look at the residual errors resulting by applying Laplace noise to each of these counts here, we can notice that essentially all the errors are uniform across all counts and the variants are uniforms as well. As soon as we are projecting those counts onto the non-negative simplex, then we notice that the residual errors change and there are some parts of the errors generally decrease. When we are also adding these other linear constraints, still within the same privacy budget, then we notice that those errors further reduce. This is actually an observation that several other groups have made already in the past. But what is interesting here is that, as you notice, the variance here changes differently in different subgroups. So it may create some disproportionate effect. And in particular, there are some groups, some counts, which will be biased positively and other one which will be biased negatively. So why this is happening? I spare you the suspense. This is happening because of the non-negativity constraints. In fact, we prove that for some classes of linear programs that do not involve non-negativity constraints, you can still construct unbiased estimators of those solutions. And so in a work last year, we were able to quantify the bias due to certain classes of projection mechanisms. And this result here essentially tells us that, it relies on showing that there exists an L1 ball of a certain radius centered around the data point of interest, which is a feasible subspace for which there is no bias. And so we can then quantify the probability of lying outside this ball here. And this is illustrated in this figure on the bottom, where we are showing for two different counties the errors induced by a Laplace mechanism on those counts in blue, and the error introduced after we post-process the data. So you see the bias here. You see how we are producing this bump around 0. Now, look at how this bias will disappear when we are progressively shifting. So we're adding counts to every entity here by 5, by 15, and so on. And so what we are effectively doing here is enlarging this radius and so enhancing this feasible subspace. So what does this mean in practice? This means that post-processing reduces the variance of noise differently in different regions. So regions with many subregions, think at states and then counties, they will have more variance than regions with fewer subregions. And so this creates some situations that are really undesirable sometimes, And so to give you an example, if we're aggregating counts for state of Arizona, which has 15 counties, and for the state of Texas, which has 254 counties, we'll get a difference in 6% in terms of variance. And thus this might result in strong allocation error and differences. So these results may have strong implication with respect to group fairness, and thus we're working with statistical agency about informing them about the trade-off between the granularity of the release data, the bias, and the variance. So to sum up what we have discussed about so far, essentially we have said that there are two sources of unfairness in decision tasks that rely on privacy-preserving data. The shape of the problem that we're using for allocating resources, and the post-processing operator that we're using to satisfy some data invariance. I also briefly want to talk about fairness impact in learning tasks. So the setting here is as follows. We're using a privacy-preserving learning mechanism to generate some outputs, and the data here is defined by some individual data points with a description of the feature of those data points, the membership of a group, like male versus females, and the label. And the task is the classic one. So we want to minimize an empirical risk function. What we do here is focusing to analyze fairness. We focus on the notion of excessive risk, which defines the difference between the private and non-private risk function. So very similar to what we have done for the bias. We're looking at what is the impact of privacy due onto the task accuracy or onto the task loss. And we're going to measure fairness by looking at the excessive risk gap, which looks at the excessive risk for a given group compared to the excessive risk given the population, right? So how much do male lose in terms of accuracy because of privacy with respect to how much the entire population loses because of privacy? So the first result comes, well, let's first look at output perturbation because it's a really simple setting. So output perturbation does nothing else than adding Gaussian noise to the optimal model parameters of a logistic regression problem, for example. And so the first result is an analogous for what we have showed in the decision-making context. This result here relates fairness and the difference in local curvature of the losses associated with a group. Basically, it tells us that output perturbation may introduce unfairness whenever there's local curvature associated with the loss function of different groups differ substantially one another. And it also suggests that groups with larger Hessians will have larger excessive risk compared to groups with smaller Hessians. And so we can notice this in this figure here, which is on the bank data set, where we see that the group which has larger Hessian trace has also larger excessive risk. Notice also how this relation here is attenuated when the privacy budget increases. And this is really due to the fact that when the privacy value increases, we require smaller sigma to satisfy this larger privacy budgets. And so the dependency between this excessive risk and this coefficient here is attenuated. So the first corollary here tell us that even if we're training a linear model with an L2 loss function, which is very common, we cannot guarantee pure fairness. And so this has come from the observation that the Hessian of the L2 loss for a given group depends solely on the input norms of the elements of that group. And now, interestingly, this result here highlights a relation between the fairness and the average input norms of different groups. And so when these norms are substantially different from one another, they will also impact their respective excessive risk differently. And this is really an interesting observation, and it tells us that if the norms of two groups are similar or exactly the same one another in expectation, then their output perturbation with L2 loss will achieve pure fairness. And so an interesting trick here is that of normalizing the input values of each group independently. And we try to do so, and that works pretty well to remove this type of fairness issues. So having identified the dependency between the Hessian model loss and the privacy parameters within the output perturbation, we can look at a little more complex scenario. So in the context of stochastic graded descent, here, in contrast to output perturbation, we do not restrict to convex loss functions, and the privacy analysis does not require optimality of the resulting model parameter. So DP-SGD, is a vastly adopted framework for training privately. So in a nutshell, it relies on the following steps. At each iteration, we're computing the gradients of the loss for each data samples in a mini batch, and we're clipping those gradients in a ball of size C, of radius C, and we're adding noise independently to each of those clipped gradients, averaging them, and update the parameters. So there are two key characteristics here in the DP-SGD: clipping the gradients and adding noise to those resulting clipped gradients. And we will see that both factors will affect in exacerbating unfairness in the private predictor. So I don't intend to have a text slide here, but essentially, in a nutshell, this result that we showed in ERIPS last year connects the expected loss for a given group with the excessive risk for that given group. What we can say is that the expected loss for a given group can be decomposed by three terms. The first term, which relates to model parameter updates and is not affected by private training, and other two terms that relate with an effect due to gradient clipping and an effect due to noise. And when we add it together, those terms constitute the notion of excessive risk for that group, which is what we are analyzing for unfairness. So this is really interesting because we can pinpoint directly what is the reason for higher excessive risk due to clipping and what is the reason for higher excessive risk due to noise. And we have a little schematic here that will show what is impacting what. And the main takeaway is that the gradients of the gradient norms for the particular group and the clipping bound values are the main factor that are affecting this excessive risk due to clipping component, and the Hessian loss and privacy parameters are the main factor affecting this excessive loss due to noise addition. If we can zoom in just a little bit and asking the question why clipping causes unfairness here, we essentially have this intuition, which it was shown also by other work, but by Stephen Wu, for example, last year as well, that showed, but on the errors, that they showed that clipping essentially causes some information loss. And here we notice something very similar when you have two groups, and those two groups may have different average gradients to backpropagate. Then if one group has gradients that are much larger than the overall bound C, then you can lose more information than another group, and thus causing disparity in the overall flow of information. So here, well, we provide some sufficient condition for which a group might have larger excessive risk than another, solely based on this clipping analysis. And what we show here is that the impact of gradient clipping for different clipping values on the gradient norms and on the excessive risk. And so basically we can see that the largest the clipping value, the lowest are the gradient norms. And also we can show that groups with larger gradient norms have also larger excessive risk. I want to relate once again this concept of the gradient norms here. So there is a strong correlation between input norms and gradient norms. And this is outlined by this figure. There is this correlation is especially evident, this positive correlation is especially evident during the first stages of training, and then it fades away But actually in private training, we use fewer iterations than in normal non-private training. And so this is interesting because both gradients and input norms can affect the excessive risk. And in fact, here we show that there is some positive correlation between input norms and the excessive risk for a given group, right? So what this means is that, again, if two groups of individuals have different input norms, then they can affect, they can exacerbate unfairness differently. So just because a group has larger subfeatures, this might have more excessive risk. And so this is, I think it's important for me to stress on this observation, because it's a common belief that unfairness here comes from data proportion. So if you have more male than females, then this will cause more issues in the private training. But here we're really showing that it's the distribution of data. And there are some individuals that are more the details of these distributions, and that is the reason why we're causing this type of unfairness issues. We also noticed that there is an interesting dependencies between the term caused by the noise, this excessive risk caused by the noise, and the closeness to the decision boundary of certain samples. What do we mean here? So if we look at this relation between the trace of the Hessian, which is related, to the addition of noise, and the inverse distance to the boundary, we notice a really high relation, which means that individuals whose outputs are close to the decision boundary will have higher Hessian traces, right? So local curvatures of the loss function. And so this, what is telling us essentially is that the model decision for samples that are close to the decision boundaries are obviously less robust to the presence of noise with respect to those that are farther away from the boundary. And so they suffer more this disparate impact. So why it's important to pinpoint those type of issues here, because they can help us devising some mitigating solutions. And what we attempted to do here is devise some solution which penalizes the classic empirical loss function by a term that equalizes those factors responsible for emphasizing the excessive risk due to clipping and due to noise addition for any group. And what we can show here is that when we weight those when we turn off those factors, we can have large excessive risk. But when those factors are turned on, then the excessive risk are typically smaller, and the excessive risk gap especially reduces. So some concluding remark. This talk was motivated by the continuous using of rich data sets and combined with the adoption of black box algorithms, which is sparking concerns on how those algorithms operate and how do they handle privacy and discrimination. We proved that several decision problems with significant societal impacts have inherent unfairness when applied to differential private release on census data. This is mainly due to the problem shape and to the post-processing step of the data release. We also analyzed this setting in learning tasks in the DP-SGD. We also have an analysis for PATE, which is a semi-supervised setting, but I hadn't had time to discuss here. And I think that this area here, it's really exciting and in a way still new direction. And I believe that this area really requires a close cooperation between different expertises, including CS and policymakers. So thank you. I want to thank also my students and collaborators, as well as the sponsors of my research.
Great, thanks so much. Really great talk. I'm going to stop recording now. Just gonna check if there is any questions on the YouTube chat. Doesn't look like it. So